Hi, I'm Sölvi, a postdoc in the Seismology and Wave Physics group at ETH Zurich. We published a paper recently titled Data-Adaptive Global Full-waveform Inversion, where we show how the internal structure of the Earth can be mapped in a much more efficient way than previously. When earthquakes occur, they emit waves that travel through the globe. The seismic wave fields are affected by the internal structure of the Earth in a way that the wave field gets deformed or reflected on its way to the surface. In full waveform inversion, we try to predict the shaking on the surface by modifying our model of the Earth. These predictions we can use to compare to actual shaking at the surface and use that to uncover the Earth's internal structure. The problem is that simulating seismic wave fields propagating through the Earth costs time, energy, and money. And to gather enough information, we need thousands of simulations. It is thus very important to do this as efficiently as possible, and in our paper, we've taken a big step in that direction. We've done this by combining two methods that have already been introduced on this channel. Firstly, the Wavefield adapted meshes, which were introduced in this video, and secondly, the dynamic Minibatch method, which was introduced in this video.
What we see here is a global scale Wavefield adapted mesh. It's used to simulate a global scale seismic wavefield emitted from the starred source there at the top. The meshes exploit how much smoother the wavefield is in the longitudinal direction compared to the radial one and the latitudinal one, making simulations significantly cheaper than before. For more information, scan the QR code on the left for a YouTube video on the subject, and for even more detailed information, scan the QR code on the right. The dynamic Minibatch method is a stochastic approach to full waveform inversion. Instead of using the entire dataset to compute each model update, we use mini-batches, which are subsets of the dataset. To monitor misfits between iterations, we always make sure that there's a part of batch n that continues to batch n+1. This way, we can compute multiple model updates while we are exploring the full dataset. For more information on this, scan the QR code on the left. We tested our method by creating an Earth model with minimal prior assumptions. We thus assumed that the internal structure of the Earth only varied with depth and used earthquake data to find out lateral variations. We used information from almost 1,200 earthquakes, which were recorded all around the globe, resulting in almost 3 million three-component waveforms. Here you can see our resulting Earth model at 100 kilometers depth. We can clearly see some high velocities where there are cratons in Africa, North America, Australia, and Russia. What's also apparent are the diverging plate boundaries, where we consistently observe relatively low velocities. The same can be said about hotspots, which all align themselves in low velocity regions due to the warm rising materials that explain the unusually high level of volcanisms. By going a few more kilometers down into the mantle, we stop seeing the marks of the diverging plate boundaries, and instead, we start seeing the imprints of the converging boundaries. On one side of each of these black lines, we can see high velocities which are related to the cold subducting slabs into the surrounding mantle. Remember that the initial model we used was completely feature-free, and all of these velocity variations have thus been requested by the data. Finding expected features like the subducting slabs is an indication that our method produces meaningful results. We wanted to reduce the compute cost of such a method, and we can show you how much we actually reduced it by comparing our compute cost to the cost of the same project without any of the developments that we introduced. So we did 72 iterations or model updates at the cost of only about a third of an iteration using a standard full waveform inversion approach for the exact same problem. So to conclude, we dramatically reduced the required cost of large-scale full waveform inversion, and in the process, we created a global velocity model. The model is called LOVE, which stands for Long Wavelength Earth Model, and it's available for download at the IRIS EMC repository. The inversion was fully automated from start to finish using Salvus and Inversionson.
Thanks for watching, and please check out our open access paper on the subject. We'll also put links to other relevant papers in the description below.